All right, Module 9, Nuclear Energy, Part 5. So enrichment, we have 7 forms. We talked about how we're trying to enrich it from 0.7% up to 2 to 3%. And we have the different weights. And so like I said, heavy weight is uranium-238, middle is 235, and lightweight is 235.4. 38 is considered stable. That's the one that breaks down every 4.4 billion years. 235 is the one that if I hit it with a neutron, it'll become the weight of 36 just for a moment, momentarily, a blink of an eye, and then it will bust apart because it cannot stay stable at that weight limit. And so it'll break apart and become barium and thorium. There are 3 types of enrichment method. The first one is gas diffusion, the next one is gas centrifuge, and the final one is laser separation. In the United States, the only one that we allow commercial sector to produce uranium for enrichment cores or pellet production is in the form of gas diffusion. That does not mean it's good technology. It's actually old and outdated, and a centrifuge system would be better. But we have a political issue in the United States where no politician wants to vote to change laws to allow for other forms of nuclear power uranium production within our country, because that would give them the black mark of voting for or against nuclear power, which makes them not want to have any actions. And so it's something that's being highly regulated but can't change its regulations. So we're using an outdated technology. But I'm going to explain them all. And I'm also going to say that we do laser separation, but only for military purposes in the United States, but it does occur. So on that note, gas diffusion. So I take the uranium oxide, so the UO2, and I change it to uranium hexafluoride, and that's not that hard. I just have to mix it with fluoride when I'm heating it up. So I heat up my uranium, it drops the oxygens, and it picks up the fluoride because it prefers that in its gas form. Then once I have it as uranium hexafluoride, I can push it through a cylinder system, which has porous membranes on either side. And the small uraniums, the ones that are 234 and 235, can fit through the porous membrane holes, where the uranium-238s are a little too big, and so most of it can't fit through the porous membrane holes. And therefore, I end up with this area where I have mostly 234 and 235 uranium, just enough, 2 or 3%. The rest is all uranium-238 that did squeeze its way through. And it makes the perfect number necessary, which then I can cool down and compress. And once I cool it back down, I can take it from its solid form and press it into these little pellets. And that's basically gas diffusion. The next one, gas centrifuge, is incredibly efficient. Once again, I take my uranium-235 and I make it into a gas in uranium hexafluoride. And so once I have my uranium hexafluoride, or my fluoride 6, I can then take that gas and put it into a cylinder system and spin it. The heavy stuff, the uranium-238, sticks to the outside, and the lightweight stuff stays to the inside. So it basically sets itself up based on weights or densities as it works its way out. And then I can just stick my syringe in the center and syringe out my 235 and my 234 material from the center. And then I can just cool it back down to room temperature, which puts it back in solid, and I can press it into a pellet. Last one is laser separation. This one is done with a laser system, which has an optical module and a separation module. There is no reason in a commercial sector why we would need to use laser separation unless we needed to enrich uranium at such a high level. And so this is really only needed for weapon application only. But what it is it's a laser optical system where I put my uranium hexafluoride, once again, I have it as a gas in isotopic material, into this kind of like black box system that has a laser, and it hits the fluoride particles with the laser and it bounces back, and the splay on the way that it bounces back will identify the size of the particle. And then the optical module has a digital separation system on it that basically has like a little computer inside it with a little suction, and it just suction hoses the gas modules that I need. And it sounds complicated, but it's not. It's actually a pretty simple robot to the point where some colleges have a robot that does like an optical laser system that just doesn't do the module separation part of the system, right? So it's not as complicated as a tool as it sounds, but that's the optical laser separation system. Like I said, there's no use for it in commercial application, but we do it in the United States. We do it for military application. So, optical system. That brings us to talking about our reactor core. So now I have my uranium-235 and I press it into a little pellet, and those pellets can get loaded into an assemblage of a reactor core system. And so I can take, and once again, just reviewing chain reactions, I can take and now make my fuel. So I take my uranium hexafluoride and I convert it back into uranium dioxide, so it goes back into its powder form. And then I press those that powder into pellets, and those pellets then get loaded into a zircon alloyed shaft. And the reason why it gets loaded into that sort of material is because a zircon alloyed or stainless steel shaft that is a hollow tube will allow neutrons to flow freely through them. So that means that the tube sitting next to another tube will allow a neutron to actually pass through the material from one tube to the next, so that I can create another chain reaction on the other side. So I can have actions going from pellet to pellet within the pellet itself, and from one pellet to the adjacent pellet through the tube material. Now, because of that, we need to be able to control this material, and that's where control rods come in. So here's first my little assemblage. So I have my little pellet, and that gets loaded into my fuel rod, and my fuel rod gets loaded into my assemblage. My assemblage is then spliced up, and between different assemblies, to kind of blockade them into groupings, I then put in control rods, and I'll have about 120 to 180 control rods within my assemblage. Those control rods will be made out of cadmium or boron, and the reason for that is because they capture neutrons. They like to absorb neutrons, and so if I capture the neutron, that neutron cannot go on to bombard any other uranium, making any type of chain reaction occur. And so I can stop or slow down the chain reactions by dropping my control rods in and out of my assemblage bundles, which brings me to going back to this picture that has this little setup here. This is a control rod. It's on one stem, and this stem can raise up and down within the assemblage to make the reaction occur faster, creating higher temperatures, which allows me to make more steam, which allows for more steam turbine turning. More turbine turning means that I'm turning my generator more. The more I'm turning my generator, the more electricity, right? Electrons jumping. So I can make greater amounts of electricity or lesser amounts of electricity based on the raising and lowering of my control rods. That brings me to reactor cores. Now, I had mentioned in previous slides that we have a lot of different types of ways that we produce electricity in the world. As far as nuclear reactor cores, there are smart nuclear reactors and there are mini nuclear reactors. Both of those systems are now in operation, specifically in Japan. That's the country that comes to mind right away that has these. In the United States, we allow two. We allow boiling water reactors and we allow pressure water reactors. So BWRs and PWRs. Both of them are what's called light water reactors. This can be confusing because they use a lot of water and the water that they use is called heavy water. Now, on this note, if you have not watched the videos showing a little bit about the different reactor cores, please take a pause and watch those videos. They explain more on light water reactor cores, both boiling and pressure, but I will pick up and do a quick overview of them, and then I will move on to the next sector.